Halo, Assalamualaikum warahmatullahi wabarakatuh. Pada hari ini kita akan mulai kuliah kalkulus 2. Today we want to start lecture on the second calculus. With the topic luas area datar dalam sistem koordinat Kartesius. This is actually in English the area in Cartesian coordinate. So in chapter 4 in our lecture notes, we call the topic application of definite integral. In bahasa Indonesia it is called penggunaan integral tertentu. In this chapter there are many application of the definite integral. As I told you in the outline of the topic, that in the pandemic of COVID-19, we only have 6 sessions. Let us start our first section about luas area datar. In English, it is called area, the area in Cartesius coordinate. If we have the function f continuous and non-negative at the interval ab, as we draw here in these pictures in the blue area, this area, the area R, is defined by the area restricted by the x-axis. X is equal to a, x is equal to b, and the y is equal to fx. In this lecture, we would like to find the formula of the area A, the blue one, by using definite integral. How can we do that? We can do that by the following way. First, we would like to approximate the area, the blue one, by using the partition. The partition is actually consisting of A0 is equal to A, x1, x2, x3, xi minus 1 xi until xn minus 1 until xn. Xn is actually equal to b. If we take this partition, then we have n subinterval xi minus 1 xi for I is equal to 1 until n. Here in between, between the xi minus 1 and xi, let's say we take the ti, is equal to xi star, then we have the rectangle with the height fx is star, and the weight is actually the delta xi. Delta xi is actually the xi minus 1. After we have this partition, then we make, as you know in definite integral, the sum of the partition with respect to f. That is actually the sigma f ti delta xi, where here the ti is equal to xi star, here xi star. And delta xi is actually the xi minus the xi minus I, minus 1. Once again, the delta xi is actually equal to xi minus xi minus 1. The SPF is actually the sum, this number, depending on the partition of P and depending on the function f. If we take the limit, actually the norm of P tends to 0. What does the norm of P? The norm of P is actually the maximum of the delta, the maximum of the delta xi. If we take the limit, the norm P tends to 0, then we have the n tend to infinite if the subinterval are equal and the function f is continuous. So the L, the luas, the area in English, is actually the limit of the SPF. By using the definition of definite integral, this limit tends to the area of the blue one. And by definition of the definite integral, this is actually equal to the integral, definite integral fx dx between a and b. So the conclusion is that if the function is non-negative, the f is non-negative, f is continuous on interval ab, then the area, the L, is actually equal to the integral ab fx dx. This is the formula. Of course, our question, how can we do when the function f is negative? When the function f is negative, that means the curve under the x-axis. So the value of the integral will be negative. By using this fact, if the f is negative, then we take the negative of the value of the integral is the area. So by using these two cases, we conclude that the area, of the region is equal to L, the integral a b f x dx. We take the absolute value because the integral has the negative value when the f is negative. Then we take the absolute value. So this is the negative of the value of the integral a b f x dx. That is the consequences of the area when the function f is negative. In conclusion, we can say the following. If the function f is an arbitrary function, it can be negative, it can be positive, then the area, the formula of the area is equal to L equal to A is equal to the integral AB, the absolute value of fx dx. That means equal to the integral AB fx dx when the fx is non-negative. But then when the fx is negative, then we take the negative of this number. So in conclusion, we say that the formula of the area of the flat area, the area is actually equal to the integral AB fx dx. For example, the function like this consisting of two parts. In the right side of 0, the value of the function is positive. In the left side of the 0, the function is negative. So this function is actually fx is equal to x to the power of 3. This function, if you integrate between minus p and p without any absolute value, then you have this is negative, this is positive, and they are the same value. So you have 0. of course the 0 is not the area, and the area must be take the following. In the right side of 0, we take the integrand is x power 3, but on the left side we take the minus x to the power of 3. So all of them, we can count that these two area actually equal to 2 times of the area on the right side. This is the example of this case. Secondly, in the following example, if we take the fx is equal to x squared minus 4, we have the curve like this. In the left side of 2, the value of the fx is negative. And in the right side of 2, the value of fx is positive. So be careful if we want to take the area of the shaded area, we have to count the absolute value. Otherwise, your answer will be wrong. As an illustration, general illustration, if the function g under the curve, under the x-axis, something like this, you have to take the negative value. And if the curve like this, that means the function upper the x-axis, then you have to take the absolute, not necessary to take the absolute value. So something like this is also can be counted by using the formula, the integral AP, the absolute value Gx dx, the same as the function of f. So that's all. That's the conclusion in the first session is that the area formula is actually the integral of AB, and the integral is the absolute value of integral dx. What about the formula between two curves? If we have two curves, the upper curve is y is equal to f. The lower curve is y is equal to gx. And the area A lies between two curves. By using the same way, we can easily understand that the area L of these two curves becomes the integral AB, the absolute value of fx and gx dx. That means equal to fx means gx dx if the fx is greater than gx, and the negative value of this one if the fx is smaller than gx. So that by using this formula, we have to be careful in which region fx is greater than gx, in which region fx less than gx. So before doing the calculation, you must find the interval in such a way that the fx is greater than gx, and the interval in such a way that fx is greater than gx. For example, if we want to find the area restricted by this function fx is equal to x squared between minus 1 until 3, between minus 1 until 3. As you see here in the picture, that the function fx is equal to x squared, this value all non-negative. So we do not need to take the absolute value because it is already positive. So the L is equal to the integral from minus 1 until 3 x squared dx. Yeah. It is actually equal to 1 over 3 x power 3 between minus 1 until 3. If we put minus 3 and minus 1, then we have 1 over 3 times 3 power 3 minus 1 power 3 is equal to 1 over 3 times, this is 27, this is 1. This is minus 1. Minus 1 is equal to plus 1. So altogether is 1 over 3 times 28. So the area is actually 28 divided by 3. This is the simple example. The second example is the following. If we want to find the area of the region enclosed by the graph fx is equal to x squared minus 4 between 0 and 5, be careful, between 0 and 5, then we have to look at on the picture. This picture is actually, look at it on the positive area if the x is greater than 2. And between 0 and 2, it is negative. It is actually, we call it A1, this is A2. So the area, the shaded area, is equal to area A1 and area A2. We have to count separately between these two intervals. Let me count. From A1, of course, the integral between 0 and 2, and this is minus fx, because fx has negative value. So this is equal to the negative of x squared minus 4. It is equal to minus x to the power of 3 divided by 3 minus 4 times x between 0 and 2. If we take this 0 in this x, we have minus 8 divided by 3 plus 8 equal to 16 divided by 3. On the other hand, the A2, take the fx, because the fx on these two interval between 2 and 5 is positive. So the absolute value is actually equal to itself. So this is equal to the integral of x squared minus 4 from 2 till 5. Yeah, it is equal to 1 over 3 times x to the power of 3 minus 4x between 2 and 5. If we take this interval to the variable, we have 125 divided by 3 minus 20 minus 8 divided by 3 minus 8. It is equal to 81 divided by 3. It is equal to 27. So altogether the area is equal to the A1 plus A2. It is actually A1 plus A2 equal to 97 divided by 3. This is the second example. The third example is about the function y is equal x to the power of 3. If we want to count the area between the x is equal to minus 4 until x is equal to 3, we have to look for the picture. Here between minus 4 until 0, the value of fx is negative. And between 0 and 3, the value of fx is positive. For instance, here in the left side is L1, in the right side is L2. So the area is actually the sum of the L1 and L2. But we have to be careful because in L1 it is negative, so the absolute value is negative, or the negative function itself. So the L1 is the integral of minus 4 until 0 of x power 3 dx equal to 1 over 4 x power 4 between minus 4 and 0, absolute value. So it is equal to 1 over 4 times 0 plus 4 to the power of minus 4 to the power of 4. So it is equal to 64. 64 satuan luas, 64 unit. On the other hand, the L is equal to the integral between 0 and 3 x power 3. By the same way, we have 81 divided by 4. So altogether, the area is equal to the area, the first area and the second area, equal to 81 over 4 units. I think it is clear, very clear. As we see in the previous example, it is actually the function is explicitly function, like the function fx is x power 3, fx is equal to x power 2 minus 4. That's are all explicit function. But sometimes we also have a parametric function like this. For instance, when we want to count the area in the inside of the asteroid is actually the parametric function given by x is equal to a cos t power 3. The y is b since t power 3 between 0 and 2v. And the picture look like this. This is the A, this is the B, this is the A, this is the B. In Cartesian coordinate, it is like this: x divided by A power 2 divided by 3 plus v divided by b power 2 divided by 3 is equal to 1. I think it is well known by everybody here, every student, because you can see this equation in the calculus 1. So how can we find the area of the asteroid? We want to find it by using the formula of area by using definite integral. That we will see. We will see the simplest one. When we want to count the simplest one, I think it is better if we take a number for A and B. Here in the asteroid, when the A is equal to B is equal to 8, we have the simplest one. We want to count the area of this one. Of course, the asteroid, I take this from the book of Stewart and Troy. This asteroid, the equation of asteroid, can be described equivalent way by the following. The x to the power of 2 divided by 3 plus the y power to the power 2 divided by 3 is equal to 4. We can count it easily by using simple manipulation. We can see that it is equal x divided by 8 to the power of 2 divided by 3 and plus the y divided by 8 to the power of 2 divided by 3 is equal to 1. Or in the parametric equation, x is equal to 8 cos t power 3, y is equal to 8 sin t power 3. The t between 0 and 2, 5. Yes, this is one circle. How can we count this? We can count only in the first quadrant, and then the all area is just 4 times from the area in the first quadrant. So later on we will count in the first quadrant. In the first quadrant, actually if we want to count this is A and B, I mean the B is equal to 8. Then we count the L is equally 4 times the area in the first quadrant. The integral of y dx between 0 and B, it is actually the area of the asteroid in the first quadrant. So altogether, the area is 4 times of the area in the first quadrant. Here, the integral y dx, because the y is equal to p since t to the power of 3, then dy and the dx can be submitted. Because the x is 8 times cos t to the power of 3, then the dx is equal to 3 times 8 cos t to the power of 2 times the derivative of cos, that is the minus sin t. So altogether, the dx is minus 3 cos to the power of 2 times t and time minus sin t. So that the y is the p, the y is replaced by the p since t power 3, and the dx replaced by this. So altogether it is equal to 12. Why 12? Because 3 times 4 is equal to 12. So it is equal to the 12 times a times b integral 0 until 5 divided by 2. Why? In here the integrand between 5 divided by 2 until 0. Why? Because the 0 until b, 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 that means the 0 is equal to 5, is equal to the angle 5 plus pi divided by 2, and the b is equal to 0. So that the integrand 0 become 5 plus divided by 2, and the b becomes 0. And here, because this is the minus, we want to change the plus. If we want to change from the minus to the plus, we have to change the upper bound of the integral, so that the integral will be, or the integral become 12 times a times b times the integral 0 until 5 divided by 2 of the sin t power 4 cos t power 2. So this is by using the standard formula. because the cos square t is equal to 1 plus cos 2t divided by 2, and sin square t is equal to 1 minus cos 2t divided by 2, then the integral become like this. Altogether, we put here 2 square is equal to 4, 2 square is equal to 4. So 4 times 4, so yeah, 4 times 4. So altogether become 12 divided by 8, a times b integral a 5 plus 5 divided by 2 of this 2 square. If this 2 square you calculate it, then it become 1 over 2 minus cos 4 t minus sin square 2t cos 2t dt. Altogether, this is equal to the 1 over 2 times r, 1 over 8 sinus 4t minus 1 over 6 sinus power 3 2t, from 0 to 5 divided by 2. Altogether, we will have, it is 12 divided by 8 times a times b times 1 over 2 times v over 2. Altogether equal to 3 over 8 times v times a times v units. If we take the a is equal to b equal to 8. By the same way, we can count the area of the cycloid. As you know, in the calculus 1, that the cycloid is actually the following. If we take from the book of Sullivan, actually the cycloid is the curve like this. The parametric equation is x is equal to a times t minus sin t. The y is equal to a times 1 minus cos t. If we take the t between minus infinite until infinite, that means this circle is rolling many times, infinitely many times. But if you only roll the circle one time, you have only one curve like this. As we see in many books, like in the book of Sullivan, there are many examples of the parametric equation, especially the famous parametric equation are cycloid and asteroid. We split this one because the application of the mechanic will be discussed later. Let us see another example. Let us we come back to the standard one. I mean the area of the curve, which is given by using explicit function. For instance, like this. If we have the function y is equal to 9 minus x squared, this is upper function, and in the below function is y is equal to 2x plus 1. This is the straight line. And actually, the area between the two curves is given by the area, this area, I mean the dash area. Because of this, we have to find first the intersection of these two functions. The intersection of these two functions can be found by using inequality between 9 minus x squared and 2x plus 1, which is equal to x squared plus 2x minus 8. This is equal to x minus 2 times x plus 4 equal to 0. That means x equal to 2 and x equal to minus 4. That means in the point of minus 4, this is the intersection. And the x is equal to 2, this is the intersection. So we have the point of the intersection is 2.5 here, and minus 4 minus 7. The point minus 4 minus 7. This is these are the intersection point. By using this intersection point, we can count the area between these two curves. So the L is actually equal to the integral of the above function and the below function. The above function is 9 minus x squared. The below function is 2x plus 1. If we count by using the definite integral, you can find here this number. So I don't want to calculate in detail, but if you can do that, at home. So this is the L is equal to 36 1/3 units. Okay. So these are all of 5 examples are actually the example of the area formula in Cartesian coordinate. And the integral, we take the integral with respect to x. That means the function is explicitly y is equal to fx. But sometimes, the area is not only based on the y is equal to fx, but x is equal to gy, and the restriction of integrand is y is equal to c until d. Yeah. Let us take the following example. By using the partition P between y0 until yn, of course, by using exactly the same way, we have the sum of P and G, where the G is the function of I, is equal to the sigma of G Ti delta yi. I is equal to 1 until n. And this is actually the sum square. And if we take the norm of P tend to 0, that implies the n tend to infinite, then it is equal to the integral of CD gy dE. So the formula of the area in the function y, the L is equal to integral CD gy dE when the gy is positive. But if the gy is negative, then take the negative value. Okay? So I don't want to prove in detail because the proof is actually exactly the same. For example, if we want to count or find the area between this y is equal to x squared and the y-axis, how can we do that? Because we want to make integrand in the variable y, we have to express the y is equal to x squared become x is equal to the root of the y. So the function is the square root of the y. And the integral between 0 and 4, because the integral is on the y-axis. So the L of the test area is equal to the integral 0, 5 square of y dy. It is very easy to count. It is equal to 16 divided by 3 unit. Okay. I think it is very clear. So in general, if you want to take the formula, in general, the area between two functions in the variable y, for instance, the g2 is the function on the right side, and the g1y is the function on the left side. We want to count the L, the A, which is the area lies between the G1 and the G2, is actually the integral between C and D, of the G2, the right one, minus the G1y, the left one, dy. So this is the formula if we want to count the area between two functions which is given in variable y. Here also I just want to show you the references that describe in detail the area between two graphs, something like this. This is the book of Sullivan. I don't want to read one by one, but it is only illustration in detail about the book of Sullivan. This is also the book of Sullivan. Here I want to describe one good example from Sullivan, how to find the area between two curves in trigonometric function. For example, we have the function fx is equal to sin x, and the gx is equal to cos x. The function look like this. Be careful, if we want to look at on this area, for instance between 0 and 5, you see here between 0 and 5 divided by 4, here the cos is above the sin. But from 5 divided by 2 until 5, you see here the sin is above the cos. So that if you want to find the area between these two curves, it depends on the interval. If you want to count between 0 and 5 divided by 4, you have to take the integral that cos x minus sin x. But if you want to count the area in this area, you have to count it by using integral sin x minus cos x, not the cos x minus fa. Here actually the point is equal to 5 divided by 4 and square of 2 divided by 2 is actually the intersection between sin and cos. Okay, so it is very easy. So the area, because the area and the shaded area here, I think we want to count the shaded area. The shaded area is equal to the integral from 0 until 5 divided by 4 of the cos minus sin. That can be described this one, cos 3 minus sin 5. We can count it by using definite integral very easily, and we have actually square 2 minus 1 square unit. So the most important thing in counting the area between two functions is to find first the intersection, the point of the intersection between two curves. Okay, I put many examples from the book of Sullivan, but I don't want to describe all because of the time is very limited, and we can suggest you to read it by yourself, and afterward we can take an exercise. I think that's all. The example we already give you many examples, maybe 6 examples. I think that's enough. Later on, I would like to give you exercise to be discussed in our lecture. I think for the lecture that's all. Later on, I would like to give you a trigger of the problem in order to discuss in our discussion. Terima kasih. Thank you. Assalamualaikum warahmatullahi wabarakatuh.